Picture this, a galaxy not too far from our own, swirling with secrets that challenge everything we think we know about the universe. This is the Large Magellanic Cloud, a cosmic neighbor that defies expectations at every turn. What if I told you that within this seemingly small satellite galaxy of the Milky Way, there are phenomena so strange, so baffling, that even the brightest minds in science are left scratching their heads? From glowing nebulae that outshine entire galaxies to black holes behaving in ways we can't yet explain, the Large Magellanic Cloud is a treasure trove of cosmic mysteries. In this video, we're diving deep into 25 of the most mind-bending phenomena found in this enigmatic galaxy. Each one will leave you questioning what we truly understand about the cosmos. So, are you ready to explore the unknown? Let's uncover the secrets of the Large Magellanic Cloud together. Now, let's zoom in on our first cosmic wonder, the Tarantula Nebula. Imagine a region of space so bright it outshines entire galaxies. This is no ordinary nebula. The Tarantula Nebula, also known as 30 Doradus, is a star-forming powerhouse, and its brilliance is nothing short of extraordinary. Located within the Large Magellanic Cloud, this nebula is one of the most luminous objects of its kind in the local universe. But what makes it so bright? The answer lies in its incredible rate of star formation. Unlike most nebulae, which produce stars at a relatively slow pace, the Tarantula Nebula is a cosmic factory, churning out massive stars at an astonishing speed. These stars, some of the most massive ever observed, emit intense radiation, lighting up the surrounding gas and dust in spectacular fashion. To put it simply, the Tarantula Nebula is like a fireworks display on a galactic scale, with new stars igniting and illuminating the cosmos. But here's the kicker: its brightness isn't just a result of its star formation. The nebula's proximity to us, astronomically speaking, also plays a role. At just around 160,000 light-years away, we get a front-row seat to its dazzling show. So, while other nebulae might be just as active, the Tarantula Nebula's combination of extreme star formation and relative closeness makes it a standout in the night sky. And as we'll see, this is just the beginning of the Large Magellanic Cloud's cosmic surprises. Now, let's turn our attention to another cosmic marvel that has captivated astronomers for decades: Supernova 1987A. This extraordinary event holds a special place in the history of astronomy, as it was the closest observed supernova to Earth in over 400 years. When it exploded in February 1987, it lit up the night sky, visible even to the naked eye from the southern hemisphere. But what makes Supernova 1987 a truly fascinating isn't just its brightness or proximity. It's the strange and intricate remnants it left behind. At the heart of this cosmic explosion lies a neutron star, the dense core left over after the star's collapse. Surrounding it are the iconic rings of Supernova 1987A, a set of glowing loops that have puzzled scientists since their discovery. These rings, made up of gas and dust ejected by the star before its final explosion, are arranged in a peculiar hourglass shape. The central ring, in particular, glows brightly due to the intense radiation from the supernova, creating a stunning visual that has become a symbol of this event. But the mystery doesn't end there. Over the years, astronomers have observed the rings evolving, with new structures forming and old ones fading. This dynamic behavior has provided invaluable insights into the life cycle of stars and the aftermath of supernova explosions. For instance, the shock waves from the explosion continue to interact with the surrounding material, creating a cosmic laboratory for studying how elements are forged and scattered across the universe. What's even more intriguing is that Supernova 1987A has challenged some of our existing theories about how stars die. For example, the neutron star at its center has yet to be directly observed, leading to questions about its nature and whether it might have transformed into something even more exotic like a black hole. This ongoing mystery keeps astronomers on their toes, reminding us that even the closest cosmic events can hold secrets waiting to be uncovered. As we move forward, Supernova 1987A continues to be a beacon of discovery, offering a rare glimpse into the violent and beautiful processes that shape our universe. And just like the Tarantula Nebula, it's a reminder that the Large Magellanic Cloud is a treasure trove of cosmic wonders, each with its own story to tell. Next, we'll explore another enigmatic feature of this galaxy, the ghostly LMC4 Superbubble, a vast cavity in space that defies explanation. Now, let's venture into another fascinating feature of the Large Magellanic Cloud, the ghostly LMC4 Superbubble. This colossal structure is one of the most striking examples of how the universe carves out vast spaces through the sheer power of stellar explosions. Imagine a bubble, but on a scale so immense that it spans hundreds of light years across. That's the LMC4 Superbubble, a gigantic cavity in space, hollowed out by the combined forces of multiple supernovae and the fierce stellar winds from massive stars. The formation of the LMC4 Superbubble is a story of cosmic teamwork. Over millions of years, clusters of massive stars within the Large Magellanic Cloud lived out their fiery lives, eventually exploding as supernova. Each explosion sent shockwaves rippling through the surrounding gas and dust, pushing it outward and creating a growing void. At the same time, the intense radiation and stellar winds from these stars further sculpted the region, carving out the bubble's intricate structure. The result is a breathtaking expanse of emptiness, surrounded by glowing walls of gas that tell the tale of its violent origins. But what makes the LMC4 Superbubble truly mysterious is its sheer size and complexity. Unlike smaller bubbles created by single supernova, this one is a product of multiple generations of stars, each contributing to its expansion. The walls of the bubble are not smooth or uniform. Instead, they are riddled with filaments, knots, and clumps of gas, each a remnant of the turbulent forces that shaped it. These features provide astronomers with a unique opportunity to study how energy and matter interact on a grand scale, offering clues about the life cycle of galaxies and the role of massive stars in shaping their environments. One of the most intriguing questions surrounding the LMC4 Superbubble is how it has managed to maintain its structure over such a long period. Typically, such cavities would collapse or dissipate over time, but the LMC4 Superbubble has defied expectations. Some scientists believe that the ongoing activity of nearby star-forming regions, along with the occasional injection of energy from new supernova, helps to sustain it. Others speculate that magnetic fields or other unseen forces might play a role in preserving its ghostly form. As we continue to study the LMC4 Superbubble, it serves as a reminder of the dynamic and ever-changing nature of the universe. It's not just a static relic of the past, but a living, evolving structure that continues to shape the galaxy around it. And like the Tarantula Nebula and Supernova 1987A, it highlights the incredible diversity of phenomena waiting to be discovered in the Large Magellanic Cloud. Next, we'll turn our gaze to another cosmic wonder, the enigmatic R136 star cluster, home to some of the most massive stars ever observed. Shifting our focus to another cosmic marvel, let's explore the enigmatic R136 star cluster, a dazzling collection of stars that defies our understanding of stellar limits. Nestled within the Tarantula Nebula, this cluster is a powerhouse of extreme stellar activity, hosting some of the most massive and luminous stars ever discovered. These stars are not just big, they're colossal, with masses reaching up to 200 times that of our Sun. To put that into perspective, if our Sun were a pebble, these stars would be boulders, radiating energy at a rate that's almost unimaginable. What makes the R136 star cluster truly extraordinary is its density and the sheer intensity of its stellar population. Imagine a cosmic city where skyscrapers are replaced by stars, packed so tightly that they're practically shoulder to shoulder. This cluster is a stellar metropolis with thousands of stars crammed into a relatively small region of space. Among them are stars so massive and bright that they outshine entire galaxies. These stellar giants burn through their fuel at an astonishing rate, living fast and dying young in spectacular supernova explosions. Their short lifespans, often just a few million years, make them rare and fleeting cosmic phenomena. But why is the R136 star cluster so unusual? For one, it challenges our understanding of how stars form. Current theories suggest that there's a limit to how massive a star can grow, but the stars in R136 seem to defy these limits. Some scientists believe that the cluster's unique environment, rich in gas and dust, and subject to intense gravitational forces, might allow stars to grow larger than they would elsewhere. Others speculate that some of these massive stars might actually be the result of stellar collisions, where two or more stars merge to form an even more massive object. The R136 cluster also plays a crucial role in shaping its surroundings. The intense radiation and stellar winds from its massive stars carve out vast cavities in the surrounding gas, triggering new waves of star formation. This creates a feedback loop where the birth and death of stars continuously reshape the region. It's a dynamic, ever-changing environment that offers astronomers a front-row seat to the processes that drive galactic evolution. As we study the R136 star cluster, it raises profound questions about the nature of stars and the forces that govern their formation. How do stars grow to such extreme sizes? What role do they play in the evolution of galaxies? And what can they teach us about the early universe when such massive stars were far more common? These are just some of the mysteries that make the R136 cluster a focal point of astronomical research. With its extreme stellar population and dramatic impact on its surroundings, the R136 star cluster is a testament to the awe-inspiring power of the cosmos. As we move forward, our next stop will take us to another intriguing feature of the Large Magellanic Cloud, the peculiar Henize 70 Nebula, a rare and fascinating remnant of a supernova explosion. Now, let's turn our attention to the Henize 70 Nebula, a cosmic oddity that stands out even in the already extraordinary Large Magellanic Cloud. Unlike the chaotic swirls of gas and dust we often associate with nebulae, Henize 70 presents a strikingly different appearance. It's a supernova remnant, but not just any remnant. It's shaped like a delicate, glowing bubble, a structure so rare that it captivates astronomers and stargazers alike. What makes Henize 70 so peculiar is its almost perfect spherical form. Most supernova remnants are irregular and jagged, shaped by the violent explosions that created them. But Henize 70 defies this norm, presenting a smooth, bubble-like shell that seems almost too perfect to be natural. This unique structure is the result of a supernova explosion that occurred tens of thousands of years ago, when a massive star reached the end of its life and unleashed an unimaginable burst of energy. The shockwaves from that explosion swept through the surrounding gas, compressing it into the bubble we see today. But the story of Henize 70 doesn't end with its shape. This nebula is also a treasure trove of scientific insights. Its glowing shell is rich in elements forged in the heart of the dying star, including oxygen, nitrogen, and sulfur. These elements, scattered into space by the supernova, are the building blocks of future stars, planets, and even life itself. In a way, Henize 70 is a cosmic recycler, turning the remnants of a dead star into the raw materials for new beginnings. Another fascinating aspect of Henize 70 is its interaction with its surroundings. The bubble isn't static, it's expanding, pushing against the interstellar medium and carving out a space for itself. This expansion creates shock fronts where the bubble's edge collides with surrounding gas, heating it up and causing it to glow. These shock fronts are like cosmic laboratories, offering astronomers a chance to study the physics of supernova remnants in action. The origins of Henize 70 also raise intriguing questions. What kind of star created this bubble? Was it a single massive star, or could it have been part of a binary system? Some researchers suggest that the bubble's symmetry might hint at a more complex origin, possibly involving multiple stars or unusual conditions in the surrounding gas. These questions make Henize 70 not just a beautiful object to observe, but also a puzzle that challenges our understanding of stellar life cycles. As we marvel at the Henize 70 nebula, it's a reminder of the delicate balance between destruction and creation in the universe. A star's death gives rise to a structure of breathtaking beauty, one that continues to shape its corner of the cosmos. And as we move forward, our journey through the Large Magellanic Cloud will take us to another mysterious phenomenon, the curious case of LMC-X1, a black hole binary system that defies expectations. Now, let's shift our gaze to one of the most intriguing objects in the Large Magellanic Cloud, LMC-X1, a black hole binary system that continues to baffle astronomers with its peculiar behavior. Unlike solitary black holes, LMC-X1 is part of a dynamic duo, locked in a gravitational dance with a massive companion star. This cosmic partnership creates a spectacle of high-energy phenomena, making LMC-X1 a prime target for studying the extreme physics of black holes. At the heart of LMC-X1 lies a stellar mass black hole formed from the collapse of a massive star. What makes this system so fascinating is the way the black hole interacts with its companion. The intense gravitational pull of the black hole strips material from the outer layers of the star, creating a swirling disk of superheated gas known as an accretion disk. This disk is a powerhouse of energy, glowing brightly in X-rays as the gas spirals inward, heating up to millions of degrees before vanishing into the black hole's event horizon. But LMC-X1 doesn't behave like a typical black hole binary. Its accretion disk is unusually stable, emitting a steady stream of X-rays that defies expectations. In most systems, the X-ray emissions fluctuate wildly as the accretion disk becomes unstable or clumpy. Yet, LMC-X1's disk remains remarkably smooth and consistent, a mystery that challenges our understanding of how these disks form and evolve. Some scientists speculate that the black hole's spin or the unique properties of its companion star might play a role in this unusual stability. Another puzzling aspect of LMC-X1 is the sheer brightness of its X-ray emissions. The system is one of the brightest X-ray sources in the Large Magellanic Cloud, outshining many other black hole binaries. This extreme luminosity suggests that the black hole is feeding at an extraordinary rate, devouring material from its companion star faster than most systems of its kind. But how does it sustain such a voracious appetite without disrupting the delicate balance of the binary system? This question remains unanswered, adding another layer of intrigue to LMC-X1's story. The companion star itself is no ordinary star. It's a massive, hot, and luminous object classified as an O-type star. These stars are rare and short-lived, making LMC-X1 an even more exceptional system. The interaction between the black hole and its companion creates a complex interplay of forces, from powerful stellar winds to intense radiation pressure. These forces shape the accretion disk and influence the black hole's feeding habits, offering astronomers a unique laboratory to study the dynamics of such extreme environments. One of the most exciting aspects of LMC-X1 is its potential to teach us about black hole spin. By analyzing the X-ray emissions from the accretion disk, scientists can infer the black hole's rotation speed. Preliminary studies suggest that LMC-X1's black hole is spinning rapidly, a characteristic that could provide clues about its formation and evolution. Understanding black hole spin is crucial for unraveling the mysteries of these enigmatic objects, and LMC-X1 offers a rare opportunity to explore this phenomenon in detail. As we delve deeper into the mysteries of LMC-X1, it's clear that this system is more than just a black hole and its companion. It's a cosmic puzzle, challenging our assumptions and pushing the boundaries of what we know about black holes and their behavior. And as we continue our journey through the Large Magellanic Cloud, we'll encounter another fascinating feature, the unusual bar structure of this galaxy, a feature that sets it apart from most irregular galaxies and offers new insights into its evolution. Now, let's turn our attention to another striking feature of the Large Magellanic Cloud, its unusual bar structure. Unlike most irregular galaxies which lack a defined shape, the Large Magellanic Cloud boasts a prominent bar running through its center. This feature is more commonly associated with spiral galaxies, making its presence in the Large Magellanic Cloud a fascinating anomaly that has puzzled astronomers for decades. The bar structure is essentially a dense, elongated region of stars, gas, and dust that stretches across the galaxy's core. It acts as a gravitational funnel, channeling material toward the center and fueling intense star formation. This process is crucial for the galaxy's evolution, as it influences how stars are born and how the galaxy grows over time. But why does the Large Magellanic Cloud have such a feature when most irregular galaxies do not? This question lies at the heart of ongoing research. One theory suggests that the bar may have formed as a result of gravitational interactions with the Milky Way. Over billions of years, the tidal forces exerted by our galaxy could have stretched and reshaped the Large Magellanic Cloud, giving rise to this distinctive structure. Another possibility is that the bar emerged from internal processes, such as the collective motion of stars and gas within the galaxy. Regardless of its origins, the bar plays a critical role in shaping the Large Magellanic Cloud's present and future. The bar's influence extends far beyond its immediate surroundings. It acts as a cosmic conveyor belt, transporting gas and dust from the outer regions of the galaxy toward its center. This influx of material fuels the formation of new stars and contributes to the growth of the galaxy's central regions. In fact, some of the most active star-forming areas in the Large Magellanic Cloud are found near the ends of the bar, where the density of gas and dust is highest. These regions are hotbeds of stellar activity, producing massive stars and spectacular nebulae that light up the galaxy. Interestingly, the bar also affects the galaxy's overall structure and dynamics. It helps stabilize the Large Magellanic Cloud, preventing it from becoming too chaotic or disorganized. At the same time, the bar's gravitational pull can trigger instabilities in the surrounding gas, leading to the formation of new structures like spiral arms or star clusters. This delicate balance between order and chaos is a key factor in the galaxy's evolution, shaping its appearance and behavior over time. The presence of a bar in the Large Magellanic Cloud also provides valuable insights into the diversity of galaxies in the universe. It challenges the traditional classification of galaxies into neat categories like spiral, elliptical, and irregular, reminding us that nature is far more complex than our labels suggest. By studying the bar and its effects, astronomers can gain a deeper understanding of how galaxies form, evolve, and interact with their surroundings. As we continue to explore the Large Magellanic Cloud, the bar structure stands out as a testament to the galaxy's dynamic and ever-changing nature. It's a feature that not only sets the Large Magellanic Cloud apart from other irregular galaxies, but also offers a unique window into the processes that drive galactic evolution. And as we move forward, we'll uncover yet another layer of mystery, the evidence for a dark matter halo surrounding the galaxy, a discovery that could reshape our understanding of its structure and history. Now, let's venture into one of the most enigmatic aspects of the Large Magellanic Cloud, the presence of a dark matter halo, Unlike the visible stars, gas, and dust that make up the galaxy's luminous structure, dark matter is invisible, detectable only through its gravitational effects. This mysterious substance is thought to form a vast, diffuse halo around the Large Magellanic Cloud, shaping its structure and influencing its interactions with other galaxies. The evidence for a dark matter halo comes from observations of the galaxy's rotation curve. In simple terms, the rotation curve measures how fast stars and gas move at different distances from the galaxy's center. In the Large Magellanic Cloud, the outer regions rotate faster than expected based on the visible matter alone. This discrepancy suggests the presence of additional, unseen mass dark matter that provides the extra gravitational pull needed to explain these motions. But understanding the distribution and influence of this dark matter halo is no easy task. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it incredibly difficult to study directly. Scientists rely on indirect methods such as gravitational lensing and computer simulations to map its presence and infer its properties. These techniques have revealed that the dark matter halo likely extends far beyond the visible boundaries of the galaxy, creating a vast, invisible cocoon that envelops the Large Magellanic Cloud. One of the biggest challenges in studying the dark matter halo is determining its exact shape and density. Some models suggest it's roughly spherical, while others propose it may be elongated or asymmetrical due to gravitational interactions with the Milky Way. These interactions could stretch or distort the halo, complicating efforts to create an accurate map. Additionally, the halo's density may vary, with clumps or streams of dark matter scattered throughout, further adding to the mystery. The dark matter halo also plays a crucial role in the Large Magellanic Cloud's evolution. It acts as a gravitational anchor, helping to stabilize the galaxy and prevent it from being torn apart by tidal forces. At the same time, the halo's immense gravity influences the motion of stars and gas within the galaxy, shaping its structure and driving processes like star formation. Without this invisible scaffolding, the Large Magellanic Cloud as we know it might not exist. Interestingly, the dark matter halo may also hold clues to the galaxy's past and future. By studying its properties, scientists can piece together the history of the Large Magellanic Cloud, including its interactions with the Milky Way and other nearby galaxies. These interactions could have stripped away some of the halo's dark matter, leaving behind a trail of clues that astronomers are only beginning to decipher. The presence of a dark matter halo around the Large Magellanic Cloud also has broader implications for our understanding of the universe. It supports the idea that dark matter is a fundamental component of galaxies, shaping their formation and evolution on cosmic scales. By studying the halo, scientists can test theories about the nature of dark matter itself, from its composition to its role in the large-scale structure of the universe. As we continue to explore the Large Magellanic Cloud, the dark matter halo remains one of its most intriguing mysteries. It's a reminder that much of the universe is hidden from view, waiting to be uncovered through careful observation and innovative science. And as we move forward, we'll delve into another fascinating feature of this galaxy: its globular clusters, which offer a unique glimpse into its stellar history and evolution. Now, shifting our gaze to another captivating feature of the Large Magellanic Cloud, we encounter its globular clusters, dense, spherical collections of stars that hold secrets to the galaxy's past. Unlike the ancient globular clusters found in the Milky Way, those in the Large Magellanic Cloud are surprisingly younger and richer in metals, offering a unique window into the processes that shape galaxies over time. Globular clusters are like cosmic time capsules, preserving the conditions of the era in which they formed. In the Milky Way, these clusters are typically billions of years old, dating back to the early stages of the galaxy's formation. But in the Large Magellanic Cloud, many globular clusters are significantly younger, with ages ranging from a few 100 million to a few billion years. This stark difference suggests that the Large Magellanic Cloud has experienced more recent and intense episodes of star formation compared to our own galaxy. Another striking feature of these clusters is their higher metal content. In astronomy, metals refer to elements heavier than hydrogen and helium, such as carbon, oxygen, and iron. The presence of these elements indicates that the stars within the clusters formed from gas that had already been enriched by previous generations of stars. The fact that the Large Magellanic Cloud's globular clusters are more metal-rich than those in the Milky Way points to a history of vigorous star formation and chemical evolution. But what does this mean for galactic evolution? The younger, metal-rich globular clusters in the Large Magellanic Cloud suggest that the galaxy has undergone a different evolutionary path compared to the Milky Way. While our galaxy has had a relatively quiet history of star formation, the Large Magellanic Cloud appears to have experienced bursts of intense activity, possibly triggered by interactions with other galaxies, including the Milky Way itself. These interactions could have compressed gas clouds, igniting waves of star formation and leading to the creation of these unique clusters. The study of these globular clusters also provides insights into the conditions of the early universe. Because the Large Magellanic Cloud is a smaller, irregular galaxy, its clusters may resemble those that formed in the universe's younger, more chaotic stages. By comparing them to the older, metal-poor clusters in the Milky Way, scientists can piece together how galaxies and their stellar populations have evolved over billions of years. Interestingly, the globular clusters in the Large Magellanic Cloud are not just younger and more metal-rich, they also exhibit a wider variety of shapes and structures. Some are tightly packed, while others are more loosely bound, reflecting the diverse environments in which they formed. This diversity adds another layer of complexity to our understanding of how stars and clusters come together in different galactic settings. As we continue to explore these fascinating clusters, they remind us that the Large Magellanic Cloud is not just a satellite galaxy, it's a dynamic laboratory for studying the processes that shape the universe. And with that, we turn our attention to another intriguing phenomenon: the unusually high star formation rate in the Large Magellanic Cloud, which further highlights its unique place in the cosmos. Now, let's dive into one of the most striking features of the Large Magellanic Cloud: its unusually high star formation rate. This galaxy is a bustling hub of stellar activity, producing new stars at a pace that far exceeds what we see in many other galaxies, including our own Milky Way. But what makes the Large Magellanic Cloud such a prolific star factory? The answer lies in a combination of factors that create the perfect conditions for star birth. One key factor is the abundance of gas and dust in the Large Magellanic Cloud. Unlike the Milky Way, which has a more settled and organized structure, the Large Magellanic Cloud is rich in raw materials for star formation. Its interstellar medium, the gas and dust between stars, is denser and more turbulent, providing the fuel needed to ignite new stars. This chaotic environment allows gas clouds to collapse under their own gravity, forming the seeds of future stars. Another contributing factor is the galaxy's history of interactions with other galaxies, particularly the Milky Way and the Small Magellanic Cloud. These gravitational encounters have stirred up the gas within the Large Magellanic Cloud, compressing it and triggering waves of star formation. Imagine a cosmic dance where the gravitational pull of neighboring galaxies acts like a giant mixer, churning the gas and dust into regions ripe for stellar birth. The Large Magellanic Cloud also boasts a unique population of massive stars, which play a crucial role in driving star formation. These stars, though short-lived, are incredibly powerful. Their intense radiation and stellar winds push on surrounding gas clouds, creating shock waves that can compress the gas further and spark the formation of new stars. It's a self-sustaining cycle. Massive stars beget more stars, ensuring that the galaxy remains a hotbed of activity. Interestingly, the star formation rate in the Large Magellanic Cloud isn't uniform across the galaxy. Some regions, like the Tarantula Nebula, are particularly active, producing stars at an astonishing rate. These areas are often associated with supergiant molecular clouds, vast reservoirs of gas and dust that serve as the birthplaces of stars. The Tarantula Nebula, for example, is one of the most luminous star-forming regions in the local universe, a testament to the galaxy's dynamic nature. But why does this matter? The high star formation rate in the Large Magellanic Cloud offers scientists a unique opportunity to study the processes that drive star birth in a galaxy that's relatively close to us. By observing these processes in action, researchers can gain insights into how stars form in different environments, from the early universe to the present day. The Large Magellanic Cloud acts as a cosmic laboratory, helping us piece together the story of how galaxies evolve over time. As we continue to explore this fascinating galaxy, its high star formation rate reminds us that the universe is anything but static. It's a place of constant change and renewal where stars are born, live out their lives and eventually die, enriching the cosmos with the elements that make up everything we see around us. And with that, we turn our attention to another intriguing feature of the Large Magellanic Cloud, the peculiar magnetic fields that weave through its structure, adding yet another layer of mystery to this cosmic neighbor. Now, let's shift our focus to something truly fascinating: the bizarre magnetic fields that permeate the Large Magellanic Cloud. Unlike the magnetic fields we're familiar with in our own Milky Way, those in the Large Magellanic Cloud are anything but ordinary. These magnetic fields are not only stronger in some regions, but also exhibit an unexpected alignment that has left scientists scratching their heads. What makes these magnetic fields so peculiar, and why do they defy our current understanding of galactic magnetism? To begin, magnetic fields in galaxies are typically thought to follow a predictable pattern, often aligning with the galaxy's spiral arms or overall structure. But in the Large Magellanic Cloud, the magnetic fields seem to have a mind of their own. Observations reveal that these fields are not neatly aligned with the galaxy's bar or its star-forming regions. Instead, they appear to twist and turn in ways that challenge existing astrophysical models. This unusual behavior raises questions about how magnetic fields form and evolve in galaxies, especially those with irregular shapes like the Large Magellanic Cloud. One possible explanation for this anomaly lies in the galaxy's turbulent history. As we've seen earlier, the Large Magellanic Cloud has undergone numerous interactions with the Milky Way and the Small Magellanic Cloud. These gravitational encounters may have disrupted the galaxy's magnetic fields, causing them to realign in unexpected ways. Think of it like stirring a pot of soup. Each gravitational interaction acts as a cosmic spoon, churning the magnetic fields into a chaotic but intriguing pattern. Another factor that sets the Large Magellanic Cloud apart is its high star formation rate, which we explored earlier. The intense radiation and stellar winds from massive stars can influence the surrounding magnetic fields, amplifying them or altering their direction. In regions like the Tarantula Nebula, where star formation is particularly active, the magnetic fields are likely shaped by the powerful forces unleashed by young, massive stars. This interplay between star formation and magnetism adds another layer of complexity to the galaxy's already dynamic environment. But why does this matter? Magnetic fields play a crucial role in shaping the evolution of galaxies. They influence the movement of gas and dust, regulate star formation, and even affect the trajectories of cosmic rays. Understanding the magnetic fields in the Large Magellanic Cloud could provide valuable insights into how these forces operate in different galactic environments. It could also help scientists refine their models of galaxy formation and evolution, shedding light on the processes that govern the universe on a larger scale. The peculiar magnetic fields of the Large Magellanic Cloud remind us that there's still so much we don't understand about the cosmos. They challenge our assumptions and push us to rethink the fundamental principles of astrophysics. As we continue to study this enigmatic galaxy, its magnetic fields serve as a reminder that the universe is full of surprises waiting to be uncovered. And with that, we turn our attention to another mysterious feature of the Large Magellanic Cloud, the ghostly LMC Ghost Nebula, a faint and elusive structure that holds its own secrets. Now, let's venture into the shadowy depths of the Large Magellanic Cloud to uncover the secrets of the LMC Ghost Nebula. This faint, almost ethereal structure is one of the most enigmatic features of the galaxy, earning its name from its ghostly appearance. Unlike the vibrant, glowing nebulae we often associate with star-forming regions, the Ghost Nebula is a subtle, wispy presence that seems to hover in the cosmic background, barely visible against the tapestry of stars. What makes the Ghost Nebula so intriguing is its elusive nature. It doesn't emit the bright light or vivid colors typical of other nebulae. Instead, it appears as a faint, diffuse cloud, almost like a cosmic whisper. This subtlety has made it a challenge for astronomers to study, but it also raises fascinating questions about its origins. Is it the remnant of an ancient supernova, a shell of gas left behind after a star's explosive death? Or could it be a region of cold, dense gas, quietly waiting to collapse and ignite new stars? The answers remain shrouded in mystery. One theory suggests that the Ghost Nebula might be a supernova remnant, the lingering echo of a massive star that ended its life in a spectacular explosion. If this is the case, the nebula's faint glow could be the result of shock waves traveling through the surrounding gas, heating it just enough to emit a dim light. Another possibility is that it's a reflection nebula where starlight scatters off dust particles, creating a faint, ghostly glow. Both scenarios paint a picture of a structure shaped by the violent and dynamic processes that define the life cycles of stars. But the Ghost Nebula's significance goes beyond its origins. Its faint presence serves as a reminder of the delicate balance between visibility and obscurity in the cosmos. While some celestial objects demand attention with their brilliance, others, like the Ghost Nebula, reveal themselves only to those who look closely. This makes it a symbol of the hidden wonders that lie within even the most familiar galaxies, waiting to be discovered by patient observers and advanced instruments. Studying the Ghost Nebula also offers valuable insights into the interstellar medium of the Large Magellanic Cloud. Its faint glow and structure provide clues about the distribution of gas and dust in the galaxy, as well as the processes that shape these materials over time. By piecing together the story of the Ghost Nebula, scientists can better understand how galaxies evolve and how the building blocks of stars and planets are recycled across cosmic timescales. As we ponder the mysteries of the Ghost Nebula, we're reminded once again of the endless surprises the universe has in store. This faint, ghostly structure may not be as flashy as some of its neighbors, but its quiet presence holds a wealth of secrets waiting to be uncovered. And with that, we turn our gaze to another remarkable feature of the Large Magellanic Cloud, the supergiant shells, massive structures that tell a story of stellar winds, supernova, and the forces that shape galaxies. Now, let's shift our focus to one of the most awe-inspiring features of the Large Magellanic Cloud. The supergiant shells, these colossal structures stretching hundreds of light years across, are like cosmic fingerprints marking the galaxy's turbulent history. Formed by the combined forces of stellar winds and supernova explosions, supergiant shells are a testament to the immense power of stars and their ability to reshape the very fabric of their surroundings. Imagine a star many times more massive than our Sun, burning through its fuel at an astonishing rate. As it nears the end of its life, it unleashes powerful stellar winds, streams of charged particles that sweep through space, pushing gas and dust outward. When such a star finally explodes as a supernova, The shock waves from the explosion further compress and heat the surrounding material, creating vast bubble-like structures. Over time, these bubbles can merge, forming the enormous supergiant shells we observe today. These shells are not just remnants of stellar activity, they are active participants in the galaxy's evolution. By carving out vast cavities in the interstellar medium, they influence where and how new stars can form. The dense walls of these shells, compressed by the shockwaves, often become the birthplaces of new stellar nurseries. In this way, the death of one generation of stars can pave the way for the birth of another, creating a cosmic cycle of creation and destruction. One of the most fascinating aspects of supergiant shells is their sheer scale. Some of these structures are so large that they dominate entire regions of the Large Magellanic Cloud, their presence detectable even from millions of light-years away. Their size and complexity offer astronomers a unique opportunity to study the interplay between stars and their environments on a grand scale. By analyzing the gas and dust within these shells, scientists can piece together the history of star formation and the forces that have shaped the galaxy over billions of years. But the story of supergiant shells doesn't end with their formation. These structures continue to evolve, interacting with other features of the galaxy, such as magnetic fields and neighboring star clusters. Over time, they may collapse under their own gravity, triggering new waves of star formation, or they may dissipate, their material blending back into the interstellar medium. This dynamic process highlights the interconnectedness of all cosmic phenomena, where every event, no matter how distant or ancient, plays a role in the ongoing story of the universe. As we explore the supergiant shells of the Large Magellanic Cloud, we're reminded of the galaxy's vibrant and ever-changing nature. These massive structures are not just relics of the past, they are living, breathing entities, constantly reshaping the galaxy and influencing its future. And with that, we turn our attention to another intriguing feature of this cosmic neighbor, the abundance of carbon stars, which offer yet another glimpse into the galaxy's unique character. Now, let's turn our gaze to another fascinating feature of the Large Magellanic Cloud, its abundance of carbon stars. These peculiar stars, glowing with a deep red hue, are a striking contrast to the more common stars we see in our own galaxy. But what makes carbon stars so special, and why does the Large Magellanic Cloud seem to have so many of them? Carbon stars are a type of late-stage star where carbon has become the dominant element in their outer layers. This happens when older stars, particularly those with masses between 1 and 8 times that of our Sun, reach the end of their lives. As these stars burn through their fuel, they begin to fuse helium into carbon in their cores. Over time, convection currents carry this carbon to the surface, where it forms molecules like carbon monoxide and carbon-rich dust. This process gives carbon stars their distinctive reddish color and makes them some of the most chemically complex objects in the universe. What's truly intriguing is that the Large Magellanic Cloud appears to host an unusually high number of these carbon stars compared to other galaxies. One reason for this lies in the galaxy's unique history and composition. The Large Magellanic Cloud is smaller and less chemically evolved than the Milky Way, meaning it has a lower abundance of heavier elements like oxygen. In stars, oxygen typically bonds with carbon to form molecules like carbon monoxide, effectively locking away the carbon and preventing it from dominating the star's atmosphere. But in the Large Magellanic Cloud, the lower oxygen levels allow carbon to accumulate more freely, creating the perfect conditions for carbon stars to thrive. Another factor is the galaxy's active star-forming history. The Large Magellanic Cloud has experienced bursts of intense star formation, producing a large population of intermediate mass stars. These stars, which are the primary candidates for becoming carbon stars, are now reaching the later stages of their lives, contributing to the galaxy's high number of these red giants. Carbon stars are more than just cosmic oddities, they play a crucial role in the galaxy's evolution. As they shed their outer layers, they enrich the surrounding interstellar medium with carbon and other elements, providing the raw materials for future generations of stars and planets. This process, known as stellar nucleosynthesis, is a key part of the cosmic cycle that shapes galaxies over billions of years. The study of carbon stars in the Large Magellanic Cloud offers astronomers a unique window into the life cycles of stars and the chemical evolution of galaxies. By understanding why these stars are so abundant here, scientists can gain insights into the broader processes that govern the universe. And as we continue to explore this satellite galaxy, we're reminded once again of the intricate and interconnected nature of cosmic phenomena. With that, we move on to another mysterious feature of the Large Magellanic Cloud, the unique properties of its interstellar medium, which holds clues to the galaxy's past and future. Now, let's shift our focus to the mysterious interstellar medium of the Large Magellanic Cloud, a vast and complex web of gas and dust that fills the spaces between its stars. This interstellar medium is not just empty space, it's a dynamic and ever-changing environment that plays a critical role in the life cycle of stars and the evolution of the galaxy itself. The interstellar medium in the Large Magellanic Cloud is unique in several ways. For starters, its chemical composition is quite different from what we see in the Milky Way. The LMC has a lower abundance of heavier elements such as oxygen, carbon, and nitrogen, which astronomers refer to as metals. This lower metallicity is a result of the galaxy's younger age and less evolved star-forming history. While this might seem like a disadvantage, it actually provides scientists with a fascinating laboratory to study how galaxies form and evolve under different conditions. One of the most striking features of the LMC's interstellar medium is its density variations. Unlike the more uniform distribution of gas and dust in the Milky Way, the LMC's interstellar medium is patchy and irregular. Some regions are incredibly dense, forming thick clouds where new stars are born, while others are sparse and almost empty. These variations are driven by a combination of factors, including supernova explosions, stellar winds, and the gravitational pull of the galaxy itself. Supernova, in particular, play a major role in shaping the interstellar medium. When massive stars explode, they release enormous amounts of energy and material into their surroundings, creating shock waves that compress nearby gas and trigger the formation of new stars. At the same time, these explosions can also carve out vast cavities, leaving behind regions of lower density. This interplay between creation and destruction is a key driver of the LMC's dynamic interstellar environment. Another intriguing aspect of the LMC's interstellar medium is its magnetic fields. While magnetic fields are present in all galaxies, the ones in the LMC are unusually weak and disorganized. This lack of strong magnetic fields allows gas and dust to move more freely, contributing to the galaxy's irregular structure. It also means that cosmic rays, high-energy particles that travel through space, can penetrate deeper into the interstellar medium, influencing its chemistry and temperature. The interstellar medium is also home to a variety of molecules, from simple ones like hydrogen and helium to more complex compounds like carbon monoxide and water. These molecules act as building blocks for stars and planets, and their presence in the LMC provides valuable insights into the processes that lead to star formation. By studying the chemical makeup of the interstellar medium, astronomers can piece together the history of the galaxy and predict its future. What makes the LMC's interstellar medium truly mysterious is how it interacts with the galaxy's other features. For example, the dense gas clouds in the LMC are often found near its star-forming regions, suggesting a close connection between the interstellar medium and the birth of new stars. At the same time, the galaxy's superbubbles, huge cavities created by multiple supernovae, are filled with hot, low-density gas that contrasts sharply with the surrounding medium. Understanding the interstellar medium of the Large Magellanic Cloud is not just about studying gas and dust, it's about uncovering the forces that shape galaxies. By examining its unique properties, scientists can gain a deeper understanding of how stars are born, how galaxies evolve, and how the universe itself works. And as we continue to explore this satellite galaxy, we're reminded once again of the intricate and interconnected nature of cosmic phenomena. With that, we move on to another fascinating feature of the Large Magellanic Cloud, the curious stellar streams that weave through its outskirts, remnants of smaller galaxies it has absorbed over billions of years. Now, let's turn our attention to the curious stellar streams that wind their way through the outskirts of the Large Magellanic Cloud. These faint, ribbon-like structures are more than just beautiful cosmic features. They are the remnants of smaller galaxies that the LMC has absorbed over billions of years. These stellar streams tell a story of galactic cannibalism, offering a glimpse into the violent and dynamic processes that shape galaxies over time. Stellar streams are formed when a smaller galaxy is torn apart by the gravitational forces of a larger one. As the smaller galaxy is pulled apart, its stars are stretched into long, thin trails that orbit the larger galaxy. In the case of the LMC, these streams are evidence of its past interactions with dwarf galaxies, which it has gradually consumed. This process, known as galactic merging, is a fundamental aspect of how galaxies grow and evolve. One of the most fascinating aspects of these stellar streams is their ability to reveal the history of the LMC. By studying the motion and composition of the stars within these streams, astronomers can piece together the sequence of events that led to their formation. For example, the chemical makeup of the stars can provide clues about the original galaxy they came from, while their orbits can reveal how long ago the merger occurred. The stellar streams in the LMC also provide valuable insights into the nature of dark matter. Dark matter, the invisible substance that makes up most of the universe's mass, plays a crucial role in shaping galaxies and their interactions. By analyzing how the streams are distributed and how they move, scientists can map the distribution of dark matter in and around the LMC. This, in turn, helps us better understand the mysterious forces that govern the cosmos. Another intriguing aspect of these streams is their connection to the LMC's future. The LMC is not just a passive observer in the universe, it is actively shaping its own destiny. As it continues to interact with other galaxies, including the Milky Way, these stellar streams will play a role in determining its ultimate fate. Some astronomers believe that the LMC itself will eventually be absorbed by the Milky Way, adding its stars to the vast collection that makes up our galaxy. The study of stellar streams is not just about understanding the past, it's also about predicting the future. By examining these cosmic remnants, scientists can gain a deeper understanding of how galaxies merge and evolve over time. This knowledge is crucial for building accurate models of the universe and for understanding the processes that drive its expansion and transformation. As we explore these stellar streams, we are reminded of the interconnected nature of the cosmos. Every galaxy, no matter how small, plays a role in the grand tapestry of the universe. And as we continue to study the LMC and its stellar streams, we uncover new layers of complexity and beauty that deepen our appreciation for the wonders of space. With that, we move on to another remarkable feature of the Large Magellanic Cloud, the unusual planetary nebulae that dot its skies, each one a glowing testament to the final stages of a star's life. Now, let's shift our gaze to the glowing remnants of dying stars scattered across the Large Magellanic Cloud, the planetary nebulae. These cosmic jewels are not only breathtaking to behold, but also hold secrets that set them apart from their counterparts in the Milky Way. Unlike the familiar shapes we see in our own galaxy, the planetary nebulae in the LMC display a stunning variety of forms, from intricate spirals to asymmetrical blobs, each one a unique fingerprint of stellar evolution. Planetary nebulae are formed when a star, nearing the end of its life, expels its outer layers into space, creating a glowing shell of gas and dust. What makes the planetary nebulae in the LMC so unusual is their diversity. In the Milky Way, many planetary nebulae tend to have a more symmetrical, spherical shape, but in the LMC, they often appear more irregular, with complex structures that challenge our understanding of how these objects form. One reason for this difference lies in the chemical composition of the LMC. The Large Magellanic Cloud has fewer heavy elements like iron and oxygen compared to the Milky Way. This lower metallicity affects how stars evolve and how their outer layers are ejected, leading to the creation of these more varied and asymmetrical nebulae. The unique conditions in the LMC provide a natural laboratory for studying how planetary nebulae form under different circumstances, offering insights that can't be gained by studying our own galaxy alone. Another fascinating aspect of these nebulae is their connection to the stars that created them. The central stars of planetary nebulae, known as white dwarfs, are the dense cores left behind after a star sheds its outer layers. In the LMC, these white dwarfs often exhibit unusual properties such as higher temperatures or faster rotation rates, which may contribute to the distinctive shapes of the surrounding nebulae. By studying these stars, astronomers can piece together the final stages of stellar life and better understand the processes that shape these glowing remnants. The planetary nebulae in the LMC also serve as cosmic time capsules, preserving clues about the history of star formation in the galaxy. Because they form from stars of different ages and masses, these nebulae provide a snapshot of the LMC's stellar population over billions of years. By analyzing their light, scientists can determine the chemical composition of the original stars and trace how the LMC's star-forming environment has changed over time. What's more, these nebulae are not just relics of the past, they play a role in shaping the future of the LMC. As they expand and disperse their material into space, they enrich the interstellar medium with heavy elements, which can eventually form new stars and planets. This cycle of stellar birth and death is a fundamental process that drives the evolution of galaxies, and the planetary nebulae in the LMC offer a unique window into this cosmic dance. As we marvel at the beauty and complexity of these planetary nebulae, we are reminded of the intricate connections between stars, galaxies, and the universe itself. Each glowing shell tells a story of a star's final act, a story that is as unique as the nebula itself. And as we continue to study these celestial wonders, we uncover new layers of understanding about the forces that shape the cosmos. With that, we turn our attention to another extraordinary feature of the Large Magellanic Cloud, the bizarre gamma-ray emissions that have puzzled scientists for decades. Now, let's dive into one of the most puzzling mysteries of the Large Magellanic Cloud, its bizarre gamma-ray emissions. These high-energy bursts of light have captivated scientists for decades, offering a glimpse into some of the most extreme processes in the universe. Gamma rays are the most energetic form of light, and their presence in the LMC hints at cosmic events that push the boundaries of our understanding. One of the leading sources of these gamma-ray emissions is pulsars, rapidly spinning neutron stars that emit beams of radiation as they rotate. In the LMC, pulsars are scattered throughout the galaxy, and their intense magnetic fields can accelerate particles to nearly the speed of light, producing gamma rays in the process. These cosmic lighthouses are not only fascinating in their own right, but also serve as natural laboratories for studying the physics of extreme environments. But pulsars aren't the only suspects. Another intriguing possibility is dark matter, the mysterious substance that makes up most of the universe's mass but remains invisible to our telescopes. Some theories suggest that when dark matter particles collide, they could annihilate each other, releasing gamma rays in the process. The LMC, with its dark matter halo, provides a unique testing ground for these ideas. By studying the distribution and intensity of gamma ray emissions, scientists hope to uncover clues about the nature of dark matter itself. What makes the gamma-ray emissions in the LMC particularly fascinating is their variability. Unlike the steady glow of some cosmic sources, these emissions can fluctuate dramatically over time, hinting at dynamic processes at work. For example, gamma-ray bursts, brief but incredibly intense flashes of energy have been observed in the LMC, likely originating from the collapse of massive stars or the merger of neutron stars. These fleeting events offer a rare opportunity to study the universe's most violent phenomena in real time. The LMC's gamma-ray emissions also provide a window into the galaxy's history. By mapping where these emissions occur, astronomers can trace the locations of past supernova, star-forming regions, and other energetic events. This information helps piece together the story of how the LMC has evolved over billions of years, revealing the interplay between its stars, gas, and dark matter. As we continue to explore these high-energy mysteries, we are reminded of the incredible diversity of the cosmos. From pulsars to dark matter, the gamma-ray emissions in the LMC challenge us to rethink our understanding of the universe and the forces that shape it. Each burst of light carries with it a story of cosmic violence and beauty, waiting to be decoded by the curious minds of scientists and stargazers alike. With that, we turn our attention to another remarkable feature of the Large Magellanic Cloud. Its vibrant and active star-forming regions, where new stars are born in a dazzling display of cosmic creativity. Now, let's journey into the heart of the Large Magellanic Cloud, where the galaxy's star-forming regions come alive in a spectacular display of cosmic creation. These regions are not just ordinary nurseries for new stars, they are some of the most active and diverse in the entire universe, offering a front-row seat to the processes that shape galaxies. What sets the LMC's star-forming regions apart is their sheer intensity. Unlike the more subdued star-forming areas in our own Milky Way, the LMC's regions are bursting with activity, producing stars at a rate that defies expectations. This hyperactivity is driven by the galaxy's unique environment, where vast clouds of gas and dust collide, collapse, and ignite into new stellar systems. One of the most famous examples is the Tarantula Nebula, which we touched on earlier. But the Tarantula is just the tip of the iceberg. Scattered throughout the LMC are countless other regions where stars are born in a dazzling array of shapes, sizes, and colors. These areas are often marked by glowing clouds of hydrogen gas, illuminated by the intense radiation of young, massive stars. What makes these regions so fascinating is their diversity. In some areas, stars form in dense clusters packed so tightly that their gravitational interactions can lead to dramatic cosmic dances. In others, stars emerge more sporadically, scattered across vast expanses of space. This variety provides astronomers with a rich tapestry of conditions to study, helping them understand the many ways stars can come into existence. The LMC's star-forming regions also offer clues about the galaxy's past and future. By studying the ages and compositions of the stars being born, scientists can piece together the history of star formation in the LMC, revealing how it has evolved over billions of years. At the same time, these regions are shaping the galaxy's future, as the stars they produce will go on to influence their surroundings through stellar winds, supernova, and even the creation of new elements. But the story doesn't end there. The LMC's star-forming regions are also home to some of the most extreme objects in the universe, from massive stars that burn brightly and die young to protoplanetary disks where planets may one day form. These regions are not just places of birth, they are crucibles of cosmic evolution where the building blocks of galaxies are forged. As we explore these vibrant regions, we are reminded of the dynamic nature of the universe. The LMC's star-forming areas are a testament to the endless cycle of creation and destruction that defines the cosmos, offering a glimpse into the forces that drive galactic evolution. With that, we turn our attention to another intriguing feature of the Large Magellanic Cloud, its variable stars, whose flickering light holds the key to measuring vast cosmic distances. Now, let's shift our gaze to a different kind of stellar phenomenon in the Large Magellanic Cloud, one that flickers and pulses, revealing secrets about the vastness of the cosmos. These are the variable stars, celestial objects whose brightness changes over time, and they play a crucial role in helping astronomers map the universe. Among the most famous variable stars in the LMC are the Cepheids. These stars pulsate in a regular rhythm, growing brighter and dimmer in predictable cycles. What makes Cepheids so valuable is the direct relationship between their pulsation period and their intrinsic brightness. By measuring how long it takes for a Cepheid to go through its cycle, scientists can determine how bright it truly is. Comparing this to how bright it appears from Earth allows them to calculate its distance with remarkable precision. This method, known as the cosmic distance ladder, has been instrumental in measuring the scale of the universe from nearby galaxies to the farthest reaches of space. But Cepheids aren't the only variable stars worth noting. The LMC is also home to Ara Lyrae stars, another type of pulsating variable. These stars are older and smaller than Cepheids, but they share a similar usefulness in distance measurement. Ara Lyrae stars are often found in globular clusters, and their consistent brightness patterns make them reliable markers for determining distances within our galactic neighborhood. What's fascinating about these variable stars is how they bridge the gap between the LMC and the rest of the universe. By studying them, astronomers can not only measure distances but also gain insights into the structure and evolution of galaxies. For example, the distribution of Cepheids and Ara Lyrae stars in the LMC has helped scientists map the galaxy's three-dimensional shape, revealing its warped disk and complex dynamics. Variable stars also offer a window into the life cycles of stars. The pulsations of Cepheids, for instance, are driven by internal processes that balance gravity and radiation pressure. By studying these pulsations, researchers can learn about the internal structure and composition of these stars, shedding light on the physical forces that govern their behavior. The LMC's abundance of variable stars makes it a treasure trove for astronomers. Its relatively close proximity allows for detailed observations that would be impossible in more distant galaxies. This has made the LMC a key testing ground for refining our understanding of stellar physics and the cosmic distance scale. As we marvel at these flickering beacons of light, we're reminded of their profound significance. Variable stars are more than just cosmic curiosities. They are essential tools for unraveling the mysteries of the universe. Their rhythmic pulses echo across the cosmos, guiding us as we chart the vast expanse of space. With that, we turn our attention to another enigmatic feature of the Large Magellanic Cloud. Its dense and complex dust clouds, which play a vital role in the birth of new stars and the shaping of the galaxy itself. Now, let's venture into the shadowy realms of the Large Magellanic Cloud, where vast clouds of dust and gas swirl in intricate patterns, hiding secrets of cosmic creation. These dust clouds, far denser and more complex than those in our own Milky Way, are not just cosmic curtains obscuring the light of distant stars. They are the very cradles of new stellar life. The dust clouds of the LMC are a fascinating blend of tiny solid particles and gas, primarily composed of elements like carbon, silicon, and oxygen. These particles, often no larger than a grain of sand, scatter and absorb light, giving the clouds their dark, opaque appearance. But within these seemingly lifeless veils, the magic of star formation unfolds. What makes the LMC's dust clouds so unique is their density and structure. Unlike the more diffuse clouds in the Milky Way, the LMC's clouds are packed tightly, creating regions where gravity can take hold and pull material together. As these clouds collapse under their own weight, they fragment into smaller clumps, each one a potential seed for a new star. One of the most striking examples is the LMC's famous molecular cloud complex, known as the Tarantula Nebula's outskirts. Here, the interplay of dust and gas creates a dynamic environment where massive stars are born. The intense radiation from these young stars heats the surrounding dust, causing it to glow in infrared light, a telltale sign of active star formation. But the role of dust clouds goes beyond just forming stars. They also act as cosmic recycling centers. When massive stars reach the end of their lives and explode as supernova, they blast heavy elements forged in their cores back into space. These elements mix with the surrounding dust and gas, enriching the clouds and setting the stage for the next generation of stars and planets. The LMC's dust clouds also play a crucial role in shaping the galaxy itself. As stars form and die, their winds and explosions push against the surrounding dust, carving out bubbles and filaments that give the galaxy its intricate structure. This constant interplay between stars and dust creates a dynamic, ever-changing landscape, one that astronomers are still working to fully understand. What's truly remarkable is how these dust clouds connect the LMC to the broader universe. By studying their composition and behavior, scientists can trace the history of star formation not just in the LMC but across galaxies. The LMC's dust clouds serve as a cosmic laboratory, offering insights into the processes that drive the birth and evolution of stars everywhere. As we peer into these enigmatic clouds, we're reminded of their dual nature, both as cosmic barriers and as the very fabric of creation. They obscure our view, yet they also reveal the intricate dance of matter and energy that shapes the universe. With that, we turn our attention to another captivating feature of the Large Magellanic Cloud, its X-ray binary systems, where the interplay of stars and black holes creates some of the most energetic phenomena in the cosmos. Now, let's shift our gaze to one of the most energetic and mysterious phenomena in the Large Magellanic Cloud, its X-ray binary systems. These cosmic duos, consisting of a star and a compact object like a black hole or neutron star, are not just fascinating to observe. They are powerhouses of extreme physics, offering a window into some of the most violent processes in the universe. X-ray binaries are aptly named because they emit intense X-ray radiation, a signature of their high-energy interactions. In these systems, the compact object, whether a black hole or neutron star, pulls material from its companion star. As this material spirals inward, it heats up to millions of degrees, releasing bursts of X-rays that can outshine entire galaxies. What makes the LMC's X-ray binaries particularly intriguing is their sheer number and diversity. Astronomers have discovered dozens of these systems in the LMC, far more than expected for a galaxy of its size. This abundance provides a unique opportunity to study a wide range of X-ray binaries, each with its own quirks and behaviors. One standout example is LMC X1, a black hole binary system we touched on earlier. Here, the black hole's immense gravity strips material from its massive companion star, creating a swirling accretion disk that glows brightly in X-rays. But LMC X1 is just the tip of the iceberg. The LMC hosts other systems like LMC X3, where the dynamics between the star and black hole are even more complex, offering clues about how these cosmic partnerships evolve over time. Neutron star binaries are equally captivating. In these systems, the neutron star's intense magnetic fields and rapid rotation can produce powerful jets and bursts of radiation. Some neutron star binaries in the LMC even exhibit periodic X-ray flares, providing a rhythmic pulse that astronomers use to study their inner workings. The significance of these X-ray binaries extends far beyond their dazzling displays. They serve as natural laboratories for testing the laws of physics under extreme conditions. For instance, the intense gravitational fields near black holes and neutron stars allow scientists to probe Einstein's theory of general relativity in ways that would be impossible on Earth. Moreover, X-ray binaries play a crucial role in the cosmic cycle of matter. As material is transferred from the star to the compact object, it enriches the surrounding space with heavy elements forged in stellar cores. This process contributes to the chemical evolution of galaxies, seeding the universe with the building blocks of planets and life. the LMC's X-ray binaries also offer a glimpse into the future of our own galaxy. By studying these systems, astronomers can better understand how similar binaries in the Milky Way might behave, shedding light on the fate of stars and the role of compact objects in shaping galactic ecosystems. As we explore these high-energy systems, we're reminded of the dynamic and interconnected nature of the cosmos. X-ray binaries are not just isolated curiosities. They are integral to the grand tapestry of star formation, evolution, and destruction. With that, we turn our attention to another remarkable feature of the Large Magellanic Cloud. Its diverse stellar populations, where stars of all ages and sizes come together to paint a vivid picture of galactic history. Now, let's journey into the heart of the Large Magellanic Cloud to uncover the secrets of its stellar populations. A cosmic mosaic of stars that tells the story of this galaxy's vibrant past and present. The LMC is home to a remarkable variety of stars, from blazing young giants to ancient red behemoths, each contributing to the galaxy's unique character. One of the most striking features of the LMC's stellar populations is the abundance of young, massive stars. These stellar powerhouses, often dozens of times more massive than our Sun, burn brightly but live fast and die young. They are concentrated in regions like the Tarantula Nebula, where intense star formation is still underway. These young stars not only light up their surroundings but also play a crucial role in shaping the galaxy's structure and chemistry. Their powerful stellar winds and eventual supernova explosions enrich the interstellar medium with heavy elements, paving the way for future generations of stars and planets. But the LMC isn't just a nursery for young stars. It's also a haven for some of the oldest stars in the universe. Scattered throughout the galaxy are ancient red giants, stars that have exhausted their nuclear fuel and expanded to enormous sizes. These aging stars are relics of the LMC's early history, offering clues about the galaxy's formation and evolution. By studying their composition and distribution, astronomers can piece together the timeline of star formation in the LMC, revealing how it has changed over billions of years. What makes the LMC's stellar populations truly unusual is their diversity. Unlike the Milky Way, where stars of different ages are often segregated into distinct regions, the LMC's stars are intermingled. Young, hot stars can be found alongside ancient red giants, creating a dynamic and chaotic stellar landscape. This mixing suggests that the LMC has experienced a turbulent history, with frequent bursts of star formation triggered by interactions with other galaxies, including the Milky Way. The origins of these diverse stellar populations can be traced back to the LMC's unique environment. As a satellite galaxy of the Milky Way, the LMC has been influenced by gravitational interactions and tidal forces, which have stirred up its gas and dust, igniting waves of star formation. These interactions have also stripped away some of the LMC's outer material, leaving behind a compact but intensely active galaxy. Studying the LMC's stellar populations not only sheds light on its own history, but also provides insights into the broader processes of galactic evolution. By comparing the LMC to other galaxies, astronomers can better understand how stars form, evolve, and interact in different environments. The LMC serves as a cosmic laboratory, offering a close-up view of phenomena that are difficult to observe in more distant galaxies. As we marvel at the LMC's stellar tapestry, we're reminded of the interconnectedness of the universe. Each star, whether young or old, plays a part in the grand story of cosmic evolution, contributing to the cycles of birth, death, and rebirth that shape galaxies like the LMC. With this in mind, we now turn our attention to another extraordinary phenomenon in the Large Magellanic Cloud, the mysterious gamma-ray bursts that occasionally light up its skies, offering a fleeting glimpse into some of the most energetic events in the universe. Now, let's shift our gaze to one of the most fleeting yet powerful phenomena in the Large Magellanic Cloud, gamma-ray bursts. These sudden, intense flashes of gamma-ray light are among the most energetic events in the universe, and the LMC has been the stage for several of these cosmic fireworks. Gamma-ray bursts, or GRB, are incredibly brief, lasting anywhere from milliseconds to a few minutes. But in that short time, they release more energy than our Sun will emit in its entire lifetime. The bursts are thought to originate from cataclysmic events, such as the collapse of massive stars into black holes or the collision of neutron stars. When these events occur, they send out jets of radiation at nearly the speed of light, which we detect as gamma-ray bursts. The LMC's proximity to Earth makes it an ideal laboratory for studying these enigmatic events. One of the most famous GRBs detected in the LMC occurred in 1987, associated with the supernova known as Supernova 1987A. This event provided astronomers with a rare opportunity to observe both a supernova and a gamma-ray burst in the same galaxy, offering valuable insights into the connection between these phenomena. What makes gamma-ray bursts so fascinating is their ability to reveal the extreme conditions of the universe. The energy released during a GRB is so immense that it can outshine entire galaxies, even if only for a few seconds. By studying these bursts, scientists can probe the physics of black holes, neutron stars, and the early universe itself. The LMC's GRBs have helped refine our understanding of how these events occur and what they can tell us about the cosmos. But gamma-ray bursts are not just scientific curiosities. They also have practical implications. Because they are so bright, GRBs can be used as cosmic beacons to measure distances across the universe. By analyzing the light from these bursts, astronomers can map the distribution of matter in the universe and study the expansion of space itself. The LMC's GRBs have played a key role in these efforts, providing a nearby reference point for understanding more distant bursts. As we continue to unravel the mysteries of gamma-ray bursts, the LMC remains a vital source of information. Its unique position and history of star formation make it a hotspot for these explosive events, offering a front-row seat to some of the most dramatic moments in the universe. With this in mind, we now turn to the final phenomenon on our list, the dark nebulae of the LMC, mysterious clouds of dust and gas that obscure the light of stars and hold secrets about the galaxy's structure and history. Now, let's venture into the shadowy realms of the Large Magellanic Cloud, where dark nebulae weave a tapestry of mystery across the galaxy. These dense clouds of dust and gas, often referred to as dark nebulae, are more than just cosmic curtains. They are windows into the LMC's past and present. Dark nebulae are regions so thick with interstellar material that they block the light from stars behind them, creating patches of darkness against the glowing backdrop of the galaxy. In the LMC, these nebulae are particularly striking, offering astronomers a unique opportunity to study the raw materials of star formation. Unlike the bright, glowing nebulae we've explored earlier, dark nebulae are cold and opaque, hiding their secrets within their depths. One of the most intriguing aspects of these dark clouds is their role in the life cycle of stars. Within their dense cores, gravity pulls together gas and dust, eventually forming new stars. The LMC's dark nebulae are hotspots for this process, acting as cosmic nurseries where future stars are born. By studying these regions, scientists can piece together how stars form and evolve, shedding light on the galaxy's ongoing transformation. But dark nebulae are not just about star formation, they also hold clues about the LMC's history. The composition of the dust and gas within these clouds can reveal the chemical makeup of the galaxy at different points in time. For example, the presence of certain elements can indicate past supernova explosions, which enrich the surrounding material with heavy elements. This makes dark nebulae a kind of cosmic archive, preserving the fingerprints of the LMC's most dramatic events. What makes the LMC's dark nebulae especially fascinating is their diversity. Some are small and isolated, while others stretch across vast regions of the galaxy, creating intricate patterns of light and shadow. These variations provide insights into the conditions that shape the LMC, from the turbulence of its interstellar medium to the influence of its gravitational interactions with the Milky Way. As we conclude our journey through the 25 strange phenomena of the Large Magellanic Cloud, the dark nebulae remind us that even in the darkest corners of the universe, there is light to be found. These enigmatic clouds, though hidden from view, play a crucial role in the galaxy's story, offering glimpses into its past and shaping its future. Thank you for joining us on this exploration of the LMC's most mysterious wonders. If you enjoyed this journey through the cosmos, don't forget to like, subscribe, and hit the notification bell for more space mysteries. And as always, let us know in the comments which phenomenon fascinated you the most. Until next time, keep looking up as we wrap up our journey through the 25 strange phenomena of the Large Magellanic Cloud. It's clear that this satellite galaxy is a treasure trove of cosmic mysteries. From the dazzling brightness of the Tarantula Nebula to the enigmatic dark nebulae that cloak the galaxy in shadow, each phenomenon offers a unique window into the workings of the universe. These discoveries not only deepen our understanding of the LMC, but also challenge our assumptions about how galaxies form, evolve, and interact. The LMC's strange phenomena remind us that the universe is far more complex and dynamic than we often imagine. Whether it's the peculiar behavior of black hole systems like LMC X1, the unexpected alignment of magnetic fields, or the abundance of carbon stars, each finding pushes the boundaries of our knowledge. These mysteries are not just scientific curiosities, they are stepping stones toward unraveling the larger story of the cosmos. By studying the LMC, astronomers gain insights into processes that shape galaxies across the universe. The galaxy's high star formation rate, its unique globular clusters, and its intricate interstellar medium all provide clues about the forces that drive galactic evolution. Even the gamma-ray bursts and dark matter halo of the LMC offer tantalizing hints about the nature of some of the universe's most elusive phenomena. As we reflect on these 25 wonders, it's worth considering how much more there is to discover. The LMC is a reminder that the universe is full of surprises waiting for us to uncover them. Each phenomenon we've explored today is a piece of a larger puzzle, one that scientists are still working to solve. Thank you for joining us on this cosmic adventure. If you found these mysteries as fascinating as we do, don't forget to like, subscribe, and hit the notification bell for more deep dives into the wonders of space. And we'd love to hear from you. What phenomenon stood out the most? Do you have any theories about the LMC's strangest features? Share your thoughts in the comments below. Until next time, keep exploring and keep looking up.